All right, the IB chemistry practical exam is getting a major facelift in 2025, and today we're going to break down exactly what you need to know to absolutely crush it. So let's dive right in. So, if you've been looking at the new syllabus and feeling a little nervous about this big focus on skills, hey, you're definitely not alone. But here's the thing, this change is actually a good thing. It's designed to make you think more like a real scientist. And that's a skill that's way more valuable than just memorizing a bunch of steps. Let's use an analogy to make this super clear. The old exam, that was kind of like following a cookbook. You just had to memorize the recipes and follow them perfectly. But the new exam, it's more like a cooking competition show. You get a mystery box of ideas and equipment, and you have to prove you can apply your core skills to whip up a solid experiment from scratch. So what is this big shift really? What's at the heart of it? Well, it's a move away from just repeating experiments that you've already done a dozen times in class. See, the IB isn't just testing if you can follow a list of instructions anymore. They want to see how you think. Can you actually design an experiment? Can you look at your results and analyze them? Can you spot the flaws and solve problems as they pop up? It's a huge shift from just remembering stuff to actually doing real science. So to nail this, you're going to need a whole new game plan. It's time to stop thinking about memorizing and start thinking like a scientist. Let's break down exactly what that looks like. And the heart of that new game plan is this right here, the inquiry process. Think of this 4-step framework as your roadmap for any scientific investigation. It starts with a hypothesis, then you design a controlled experiment, you collect and process your data carefully, and finally, this is the big one, you evaluate your conclusions and all the potential errors. Okay, a huge part of concluding and evaluating is learning to speak the language of data. So let's get into the nitty-gritty skills you'll need to talk about your results, especially when they're not perfect. Right. 2 words you absolutely have to get straight in your head: accuracy and precision. Accuracy is all about hitting the bullseye. How close is your result to the actual true value? Precision, on the other hand, is about consistency. How close are your measurements to each other, even if you're way off the bullseye? And just as important is understanding the 2 kinds of errors. Systematic errors are flaws in your setup, like a scale that's always off by 5 grams. They push all your results in the same wrong direction. Random errors, though, are those little unpredictable things, like trying to judge the exact second a color changes. You can't get rid of them completely, but you can reduce their impact by doing more trials. Now, here's a core concept you just have to accept. No measurement is perfect. Not a single one. Every value you write down has some small degree of doubt, or what we call uncertainty. And showing that you can acknowledge it and calculate it, that's a key skill the IB is looking for. So this is the really crucial part. When you take those measurements and use them in a calculation, their uncertainties add up. We call it propagation. And the rules are actually pretty simple. For adding or subtracting, you just add the absolute uncertainties. For multiplying or dividing, you add the percentage uncertainties. If you can master these 2 rules, you are golden. Okay, so we've got the mindset and the math down. Now let's see how all of this stuff actually applies in the lab. We're going to walk through the core experiments that are really the backbone of this course. First up, the heavyweight champion of IB chemistry, titrations. You really need to get comfortable with these because they make up about 20% of the marks on papers 1 and 2. That's huge. And their purpose is so simple, yet so fundamental. You use a solution where you know the concentration perfectly, the titrant, to figure out the concentration of some mystery solution, the analyte. The classic mistake everyone makes? Overshooting the endpoint. Adding that 1 extra drop that turns your solution way past the target color. And the key connection you have to make is back to stoichiometry. A titration is really just stoichiometry in action. At that perfect equivalence point, the mole ratio is exactly what you'd predict from the balanced equation. Next on the list is calorimetry. This is a massive topic, especially for those data-based questions you're going to see on the exam. So you've got to know it inside and out. Your main goal here is to measure the enthalpy change of a reaction. And you do that by tracking the temperature change of the stuff around it, usually some water, and then using that famous equation, Q equals mc delta T. And this brings us right to the single biggest challenge with calorimetry, heat loss. It's just inevitable. Your little coffee cup setup isn't a perfectly isolated system. The theoretical link here is, of course, energetics. You're using real, messy experimental data to calculate a really fundamental value, the enthalpy change, delta H, of the reaction. And finally, let's look at another super important technique, colorimetry, which you might also hear called spectrophotometry. This technique is just so cool and powerful. It lets you figure out the concentration of something just by shining a light through it and seeing how much of that light gets absorbed. Basically, the more color, the more light it absorbs, and the higher the concentration. It's that simple. Now, one key thing to watch out for is that this nice straight-line relationship between absorbance and concentration can start to fail if your solution gets too concentrated. And the entire scientific foundation for this whole technique is the Beer-Lambert law, which is the equation that connects absorbance to concentration. Okay, we've gone over the new mindset, we've walked through the core experiments. Now, let's pull this all together into a solid winning strategy for exam day. Here it is, your winning checklist. First, don't just list the steps of what you did. Explain why each step is important. Second, don't just name the errors. Analyze exactly how they affected your final number. Third, don't just say, the experiment could be improved. Suggest specific, practical things you could do differently. And last but not least, you have got to master those uncertainty calculations. You know, when it all comes down to it, you have to shift your entire mindset. This exam isn't about finding the one right answer. It's about building a strong, logical, evidence-based argument for the answer you found. The real question isn't, what did you get? It's, how well can you defend it? If you can master that, you're going to do great.